Welcome to this session. This session, we are going to do the second problem on Jacobian of implicit functions. So we have u cubed plus v plus w equals to x plus y squared plus z squared. And then u plus v cubed plus w equals to x squared plus y plus z squared. And lastly, u plus v plus w cubed equals to x squared plus y squared plus z. So we have to prove that the Jacobian of u, v, w with respect to the variables x, y, and z is given by this quotient. So what we'll do is that we'll rearrange this equation to get f1, taking all these terms to the left-hand side, take these terms to the left-hand side to get f2, take these terms to the left-hand side to get f3. So a solution so from the first one, you have taking all the terms to the left-hand side, so we'll have f1 will be u cubed plus v plus w minus x minus y squared minus z squared. And then from the second one, take every variable on the right-hand side to the left-hand side. So we'll have u plus v cubed plus w minus x squared minus y minus z squared. And then f3, take every term on the right-hand side of the third expression or equation given to get u plus v plus w cubed minus x squared minus y squared minus z. So that's the first step. We are simply taking these terms to the left-hand side, this term to the left-hand side, this term to the left-hand side to define those f1, f2, and f3. So there are two Jacobians for us to evaluate. So the first one is to define Jacobian of f1, f2, f3 with respect to the variables x, y, and z. And by definition, this is given by partial f1, partial x, partial f1, partial y, partial f1, partial z, partial f2, partial x, partial f2, partial y, partial f2, partial z, and partial f3, partial x, partial f3, partial y, partial f3, partial z. So this is the definition of determinant. This is the definition of the Jacobian of f1, f2, f3 with respect to x, y, and z. And then differentiating those functions should get partial f1, partial x to be minus 1. Partial f1, partial y is minus 2y. Then the other one would be negative 2z. And then we have minus 2x, and then minus 1, and then minus 2z, and then we have minus 2x, and then we have minus 2y, and then we have minus 1. Please confirm those values from these functions. It's not hard to get the derivatives for partial derivatives for f1, f2, f3. Now, to evaluate this determinant, we use properties of determinants. So in the first row, we have a scalar, -1, which is common to all the terms. So I can factor out -1. And then I have 1, 2, y, and 2z. In the second row, I also have another scalar. So I also factor it, that factor -1. So I'll have 2x, 1, and then 2z. Similarly, this one, I have a scalar. a factor -1 for all the elements in this row. So I also factor it out, -1. So 2x, 2y, 1. So the advice is that please revisit your work on determinants to see how those properties can help you to reduce a determinant when you're finding the Jacobian. So this will be -1, 1, 2y, 2z, and then 2x, 1, 2z, 2x, 2y, 1. And we can evaluate this 3 by 3 determinant using the first row. The sign of this element is plus, minus, plus. So I'll have -1, and then this determinant positive, -1, then I have 1 times the determinant, 1, 2y, 2z, 1, minus 2y, determinant 2x, 2x, 2z, 1, plus 2z, determinant 2x, 1, 2x, 2y, which will give me, remember this is the Jacobian of F1, F2, F3 with respect to the variables x, y, and z. So I'll have -1 into, so this will be 1 minus 4 yz minus 2y into 2x minus 4 xz plus 2z into 4xy minus 2x. And then I'll have -1 into 1 minus 4 yz minus 4xy plus 8xyz, just opening the brackets, plus 8xyz minus 4xz. Now, you see this will be -1 into 1. So I can say minus 4 into yz plus xy plus 4xz. So when I factor out negative, these signs will be plus, and then plus, this will be 16 xy z. And you see when I open the brackets, I'll have -1, now plus 4 into yz plus xy plus, now there's no 4 here because it was already factored. So this is just xz. xz, and then plus 60, minus, because the negative, minus, because we are multiplying every term by -1, minus 16 xy z. So this is the Jacobian of F1, F2, F3 with respect to the variables x, y, and z. Now the last, we have to get the Jacobian of F1, F2, F3 with respect to u, v, and w. This by definition is a determinant, partial f1, partial u, partial f1, partial v, partial f1, partial w, partial f2 partial u partial f2 partial v partial f2 partial w partial f3 partial u partial f3 partial u partial f3 partial u. This is v and then this w. Now, when you work out this from the functions f1, f2, f3, you should be able to get 3u squared, 1, 1, 1, 3, v squared, 1, 1, 1, 3, w squared. And that determinant using the first row will be 3u squared times the determinant 3v squared 1, 1, 3 w squared minus 1 times determinant 1, 1, 1, 3 w squared plus 1, 1, 1, 3 v squared 1. So this is how we find this 3 by 3 determinant. So 3u squared into, this is 9v squared w squared minus 1 into 3w squared minus 1 plus 1 into 1 minus 3v squared. Remember, this is the Jacobian of f1, f2, f3 with respect to u, v, w. So when you open, you get 27 u squared, v squared, w squared minus 3 u squared minus 3 w squared, now plus 1 minus 3 v squared, which can be written as 2 minus 3 into u squared plus w squared plus v squared plus 27 u squared, v squared, w squared. So therefore, from definition, since the Jacobian of u, v, w with respect to x, y, z is given by -1. So because now we are dealing with 3 functions or 3 functions in the determinant, so this n is 3, and then we have partial f1, f2, f3, partial x, y, z divided by partial f1, f2, f3, partial u, v, w. Now, with what we have, this is the denominator, and then we had the numerator. And this one, remember, is -1. So we have -1 times -1 plus 4 into yz plus zx plus xy, and then minus 16 xyz divided by this one. We have 2 minus 3 into u squared plus v squared plus w squared plus 27 u squared, v squared, and w squared. So when you open multiply by negative sign. So we'll have 1 minus 4 into yz plus zx plus xy, now plus 16 xyz over 2 minus 3 u squared v squared plus w squared plus 27 u squared v squared w squared. And this is what we want to show that is the Jacobian of u, v, w with respect to x, y, z. So that's the proof of that problem. Thank you.